So question 10, use an algebraic method to find the square roots of that complex number. This is great, isn't it? Because they're giving 6 marks for one of those standard things that you can count on being an So just like we just talked about the determinant of a 3 by 3, finding the square roots of a complex number is, we should have practiced that going into the exam so much that you can just do it whatever the complex number is. Make up your own questions for it. Remember what we do. We say that x plus iy squared is 9 plus 40i. We need to find the real numbers x and y that fit that equation. So we multiply out the left hand side to get x squared plus 2xyi plus y squared I squared, so that's minus y squared is 9 plus 40i. We compare real and imaginary parts, so it gives us 2 equations, one that says x squared minus y squared is 9, and one that says that 2xy is 40, so xy is 20. And we need to establish those 2 equations first. I think we got 2 marks for doing that. And now we need to solve them. So I am going to say that this equation here says that y is 20 over x. I'm going to substitute that into the first equation. X squared minus 20 over x squared is 9. Be really careful because it's easy to drop marks just through little mistakes as you go through this. So here, x squared minus 400 over x squared is 9. It's kind of really easy at that point, isn't it, to forget to square the 20 on the top. So the 20 over x squared at that point. Multiplied by x squared, x to the 4 minus 400 is 9x squared, so x to the 4 minus 9x squared minus 400 is 0. We have to solve that stealth quadratic. We can think about it if we want to as being y squared minus, not y, t squared minus 9t minus 400. We wouldn't expect it to be so hard that it wouldn't factorise. You may need to apply the formula to this. But hang on, 400, are there any numbers that go into that? We need 2 numbers that multiply to give 400 and add to give 9. Well, 400 is 16 times 25, isn't it? That kind of leaps out. It might not leap out at you, but it kind of comes out as being a possible solution to this. So this is x squared, what would it need to be? Minus 16? No. It needs to be a plus 16, I think. X squared minus 25 and x squared plus 16. Is that right? As being our solution to this. So x is plus or minus 5. Remember, I did say it at the start of this, the whole point of setting it up as being x plus iy is x and y have to be real numbers. So we ignore the x equals plus or minus the square root of minus 16 as a solution. We've got those two. Y was 20 over x. So if x equals 5, y equals 20 over 5, which is 4. If x equals minus 5, y equals minus 4. And so the numbers we are looking for are 5 plus 4i, and what's supposed to be minus there? Minus 5, minus 4i. They are the roots, the square roots of that number. 6 marks, and it's a standard flow through a question, isn't it? It's something that we really ought to be practicing and knowing that we can just do whatever numbers we end up with. So that's a really nice 6 marks at the end there. Show that 9 plus 40i is a root of the quadratic equation. There are a number of approaches to this, any of which are perfectly acceptable. So I think a couple of you used the quadratic formula on z squared minus 18z plus 1681. It's a bit messy because the numbers are quite big, but you showed that if you do that, one of the roots is 9 plus 40i, and that's fine. I did it, I thought I'd do it the other way round. So I'd say if we let z be equal to 9 plus 40i. So the board's just decided to reset. Then we need to work out z squared. In order to do anything with this, z squared would be 9 times 9, that's 81. 9 40s are 360, so that's plus 720i plus 40 squared times I squared, so that's minus 1600. So z squared is minus, what is that? Minus 1519, that'd be right. Where the 7 came from, plus 720i. And we need to show that this gives us 0, z squared minus 18z plus 1681 equals, this is the factor theorem, isn't it? This is subbing in our value and showing that it gives us an answer of 0 when you put it in. That's that is z squared minus 18z plus 1681, and we have to show that that gives us 0. Minus 1519, take away 18 lots of 9 is minus 1681. That's a remarkable coincidence, isn't it? And then we've got plus 720i, and then 18 times 40 gives us minus 720i, so that equals 0. Therefore, 9 plus 40i is a root. There we go. I know it feels like that's a slightly long-winded way of doing it, but either it was only 1 mark for showing it. And you could either use sum and products of the roots, or you could solve the equation, or substitute it in. I substituted it in. However you want to do it. Now, the final part. Only 4 marks, but it does feel like it has a complicated start to it, and it's just slightly long-winded, all of this. By using the substitution, z equals 1 over u squared, find the roots of this equation. So that's the equation we've got to find the roots of. Giving your answer in the form x plus iy. Right. So I might go to a new page for this. Z equals 1 over u squared. And the equation that we're trying to solve is 1681 to 4 minus 18u squared plus 1 is 0. Okay? So if that's the substitution, actually that substitution is the same as saying that u squared is 1 over z. So I'm going to use that. It's the same substitution, isn't it? It's just rearranging it slightly. So I'm going to sub that in. That is 1681 times 1 over z squared minus 18 times 1 over z plus 1 is 0. If I multiply everything by z squared, I get 1681 minus 18z plus z squared is 0. I recognise that equation. That's the equation that we have just checked in part 2. That's that equation. And 9 plus 40i is a root of it. So the roots of that are 9 plus 40i, and because that's one of the roots, the other root must be 9 minus 40i. It must be the complex conjugate of it, because that's how roots work. They go in conjugate pairs. So they are the values of z. We're supposed to be finding the values of u. And what we now know is that u squared is 1 over z. That means that u squared is 1 over 9 plus 40i and 1 over 9 minus 40i. So u is plus or minus the square root of 1 over 9 plus 40i and plus or minus the square root of 1 over 9 minus 40i. This is, we're all establishing what u is at the moment. That's a horrible form, we wouldn't leave it in that form. We need to get it into, it doesn't actually say it, oh, it does say, give your answers in the form x plus iy. So we've got what u is, but we're some way away. Oh, but hang on, at the start of the question, we worked out the square roots of 9 plus 40i. That was part 1. So now we need to use our answer to part 1. So u is the square root of 9 plus 40i was 5 plus 4i. It's plus or minus 5 plus 4i that we got. So that's 1 over 5 plus 4i, or 1 over minus 5 minus 4i. Remember, part 1 had 5 plus 4i and minus 5 minus 4i. Now the other one is the complex conjugate of that. So this expression here gives us 1 over 5 minus 4i and 1 over minus 5 plus 4i. It really feels like we're getting somewhere, but we're still not in the form x plus yi. We now have to rationalise the denominator kind of thing of that to stop it being a complex denominator. 1 over 5 plus 4i times 5 minus 4i over 5 minus 4i gives us 5 minus 4i on the top, and it gives us 25 plus 16. Remember, it's 5 squared, the I bits cancel out, minus 16i squared, so plus 16. So this is 5 over 41 minus 4 over 41i. We've actually got, in the form x plus iy, one of the roots. We now need to recognise the pattern that the others would take, and it will all just work in the same pattern, so we don't need to do all these calculations again. You can do if you want to check it, but we don't really need to. This one is all negative, so the other root must be minus 5 over 41 plus 4 over 41i. That's that one multiplied by 1, minus 1. We've now got these ones to deal with. If this was 5 minus 4i, we would have multiplied top and bottom by 5 plus 4i. We still would have got 41 on the bottom, but we would have had 5 over 41 plus 4 over 41i. And the other root is the negative of that, so the other one is minus 5 over 41 minus 4 over 41i. There we go, they are our 4 roots. I've not presented my answer particularly in a nice way there, but there they are for us to see. Okay, and that was it. And that's maths.